Okay, so in this video we're going to be looking at solving linear equations, which certainly should be something that by now you're quite familiar with, but let's just clarify some ideas here. So the aim of equation solving is to find the value of the polynomial which makes the equation true. So for example, x equals 2 is the solution to 6x minus 5 equals 7, because if you let x equals 2 in that relationship, in that equation, it makes the equation true. If I substitute x equals 2 in place of x here, 6 times 2 is 12, minus 5 is 7. The equation is true. That's why x equals 2 is the solution to that equation. The key thing to remember when we're solving equations is that in order to keep the equality true, we must always do the same thing to both sides of the equation. And it's not about doing the same thing to a bit of the left-hand side and all of the right-hand side. You've got to do the same thing to the entire equation in order to make sure that it is still an equivalent equation. Otherwise, you've created a whole new equation, and the solutions to that equation aren't necessarily the solutions to the original equation. I know it sounds really simple, but the number of times that you will inadvertently, without thinking about it, not actually do the same thing to both sides or the same thing to everything in the equation, it will be quite frequent. Okay, so all linear equations can be solved using the following sequence of steps, and I encourage you, I'm not saying that this is the only way that you can do it, but I encourage you to be a bit systematic about how you go about equation solving, particularly once the equations start to get a bit complicated. So for me, the first priority is dealing with fractions. If the equation contains fractions, I want to deal with getting rid of the fractions first. And I have one fail-safe method that no matter whether there's one simple fraction, 10 complicated fractions, fractions on both sides, whatever, no matter what is going on with the fractions, the same method will work every time. And that is to write every term in the equation with a common denominator, and then you can multiply every term in the equation by that denominator so that you no longer have fractions. Step 2 would be to deal with any brackets, and sometimes in having completed step 1 you introduce brackets to the problem. Step 3 would be to then be about collecting like terms, and step 4 you should at that point then have a very, very simple equation doing the same thing to both sides until you get the x on its own. Okay, so let's work our way through a series of increasingly more complex examples. So solve each of the following equations for x. So it really again comes back to thinking about order of operations. We've talked about that in a recent previous video. In being able to understand how an expression is constructed. So I'm talking just about the single side of the equation that involves the unknown. You need to understand how that expression is constructed. Okay. Now I know I'm talking about a very simple equation here, and by all means fast forward if you're comfortable with this, but you need to understand how that expression is built up. So what is the first operation that happens to x? So in this instance, we start with x. X has been multiplied by 3 first, because in our order of operations, multiplication happens before subtraction, and then 5 is subtracted. So if we want to get x on its own, we need to undo those two operations by using inverse operations in the reverse order. So we have to undo the subtract 5 first. Now, you could undo the multiply by 3 first, but you would create an uglier equation involving fractions. So it's not that it's impossible to veer away from this order, but it's about making sure that if you do veer away from the order, you're still executing it correctly, and often you'll end up with a process that's not as efficient. For example, let me just take you on a slight detour. If I were to decide to divide everything by 3 first, again it's important that you remember that you must divide everything by 3. So if I want to divide by 3, I don't just get x minus 5 equals 28 divided by 3, because you've divided that by 3 and you've divided that by 3, but you haven't done anything to the middle term. Okay, so you would have to do x minus 5 thirds equals 28 thirds. Then you could add 5 thirds, and that would be a perfectly valid solution process. But you create fractions and create a more complicated expressions along the way if you don't sort of go with the more natural order. It's much more natural. The last thing that's happening to x is that 5 is being subtracted from it, so let's add 5 to both sides. That gives us 3x equals 33. And then let's divide both sides by 3, which is the opposite of multiplying by 3, so that we get x equals 11. Okay, example 2. Now it's an equation, we've got brackets here, so one of my first steps would be to expand the brackets. Now there would be another alternative here, and I'll demonstrate that in the next example, but if, for example, there wasn't a 9 over here but instead an 8, I probably wouldn't expand out the brackets on the left hand side, because the other option, other than expanding out the brackets there, is 4 is multiplying this bracket, so I could divide by 4 first. Now, if it was 8 on the right-hand side, I would do that, because 8 divided by 4 is a nice whole number. However, the fact that it's 9 on the right-hand side, I'm not going to divide by 4, because that would mean creating fractions. So I'm going to expand out the brackets on the left instead, so I'm going to have 8 minus 4x equals 9. And then again, it's about understanding what's happening here, okay? X is being multiplied by negative 4 first, multiplied by negative 4, and then we're adding on 8. If you have trouble understanding that, it might be helpful to actually rewrite that equation in a different order. It's really important to remember that any expression, is made up of sort of building blocks. So we've got 8, which is positive 8. We don't write the plus at the start if it's a plus. It's a positive 8 and a negative 4. If it suits you, so the important thing is that the sign between two terms, whether it's a plus or a minus, belongs to the term that comes after it. So you can reorder the terms as long as you keep the signs with the right terms. So it's a negative 4x and a positive 8. If it suits us and helps us to identify what's happening better, to write negative 4x plus 8 equals 9, by all means do that. Okay. So I'm going to take away 8 from both sides, so I get negative 4x equals 1, and then I'm going to divide both sides by negative 4, which is going to give me x equals negative 1/4. Now, whether you write 1 divided by negative 4, or negative 1 divided by 4, or negative 1/4, they are all the same thing, okay? Just be a bit careful about making sure that just be consistent about the way that you do it. Okay, example 3. So again, we could expand out the brackets first and get half x plus 7 on 2 equals 3. No problem with that, and that would work. However, the other way I could think about this is actually the left-hand side of that equation, the first thing happening to x is the plus 7. And the last thing happening is the multiplying by 1/2. So if I could actually focus on undoing that first. The opposite of multiplying by half is to divide by 1/2. Dividing by 1/2 is the same as multiplying by 2, multiplied by the reciprocal. So if we multiply both sides by 2, we're going to get x plus 7 equals 6, and then subtracting 7 from both sides, x equals negative 1. Okay, example 4, we've got fractions. Here's our first example where we've got fractions. And I don't mean, example 2 ended up with a fraction, but the initial equation didn't have fractions. We did have fractions here, and but because it was just half and it's half of the whole side of the equation, it was very easy to undo that just by doubling everything. Okay, example 4, I've got three different terms, all fractions with 3 different denominators. I'm going to focus first of all on writing everything with the same denominator so that I can then eliminate the fractions. So the lowest common denominator here is going to be 10. All 3 of those numbers go into 10. So I'm going to write all 3 terms over 10. Now the second term is already over 10, so we don't need to do anything to that. That's still minus 3x. The first term, the denominator was 5 and it's become 10, so we've doubled the denominator, so we must also double the numerator. 1/5 is the same as 2/10. On the right hand side of the equation, we've multiplied the denominator by 5, so we must do the same to the numerator. So 1/2 is the same as 5/10. Now that everything is over 10, what we're essentially doing is, let's multiply both sides of the equation by 10. And that's going to cancel out all those denominators, okay? So the 10 here, if we multiply that, 2/10 times 10 is 2, 3x on 10 times 10 is 3x, 5 on 10 times 10 is 5, okay? So multiplying everything by 10 is going to allow us to get rid of all of the fractions. So that's why sometimes it can feel like a slightly time-consuming step to write everything with a common denominator, but then the next step is very easy and immediately you have a very simple equation with no fractions. Okay, again, if it helps you, like we did in example 2, to write this as negative 3x plus 2 equals 5. So I'm going to take away 2 first, negative 3x equals 3, and then I'm going to divide both sides by negative 3. X equals 3 divided by negative 3, which is negative 1. Okay. Another thing to note here is I don't want to see, I would encourage you to try to get rid of things like, writing -2 on both sides. In my experience, students become inconsistent with how they write that, and they write it on one side and not the other, and then actually you've got a different equation. If you're not careful about how you write it, you potentially end up with things that mathematically aren't correct written on the page. You don't need to write it, just do it. If you're subtracting 2 from both sides, just do that, okay? Negative 3x plus 2 minus 2 is negative 3x. 5 minus 2 is 3. Just do it, okay? You don't need to signpost everything that you're doing. Alright, example 5, that's our first example where we've got more than one x term. So we need to focus on collecting the x terms together, okay? Now you've actually got two options here. You could either subtract 5x from both sides of the equation. I've just told you not to write this, but subtracting 5x from both sides of the equation, which would get rid of them over here and leave us with negative 2x on the left-hand side. Or we could subtract 3x from both sides of the equation, which would get rid of the x's from here and leave us with positive 2x on the right-hand side. I would always choose the option that keeps the coefficient of x positive if that's possible. Okay, so in this instance, I'm going to subtract 3x from both sides because I end up with positive 2x rather than negative 2x. So subtracting 3x from both sides of the equation leaves me with negative 2 on the left-hand side, and then we subtract 5x minus 3x is 2x, and we've still got this plus 5. Okay, I'm going to take away 5 from both sides because I'm now focused on getting x on its own. So x has been multiplied by 2, then we've added 5, so let's take away 5. So that's negative 7 equals 2x. And let's divide both sides by 2. I'm going to rewrite it in the other order, so I'm answering the question x equals something at the same time. So negative 7 equals 2x. We're dividing both sides by 2, so x equals negative 7 divided by 2. You can write that if you want as negative 3.5 or negative 3.5, but negative 7 on 2 is a simplified fraction. We can stop there. Okay, example 6. The place we're going to go awry here is not being careful about this negative. So this negative in here implies that we've got negative 1 times that whole second bracket. So we need to make sure that we're careful when we expand out those brackets. So expanding out the left-hand side, 3 times x plus 3 is 3x plus 9. And then we've got negative 1 times 2x minus 1. So it's negative 1 times 2x, which is minus 2x. And negative 1 times negative 1, which is plus 1. Okay. Here's the term where you'll make the error if you're not careful about what's happening with that negative there. And then the right hand side just equals 4. Let's tidy up the left hand side. So 3x minus 2x is x, 9 plus 1 is 10, so we've got x plus 10 equals 4, and then we can take away 10 from both sides. So x equals 4 minus 10, which is negative 6. Okay, question 7. Again, we've got fractions. Now, this particular fraction can be dealt with quite easily because the whole left-hand side has been divided by 2. So if we multiplied the left-hand side by 2, and obviously we have to do the same to both sides, we could get rid of the fraction. So immediately we get x plus 6 on the left-hand side, and then 2 times x minus 3 on the right-hand side, which we can expand out. Personally, I'd probably do that. However, I just want to be clear about the fact that the strategy of always writing every term with a common denominator and then getting rid of the denominators, because we're multiplying by that denominator, is always going to work. It gives you a fail-safe process. The other thing I would encourage you, if you are regularly making mistakes with these questions, follow the process of taking the time to write out the common denominator. Okay. So this is over 1, so we can write both sides of the equation over 2. X plus 6 over 2 equals, now if I write the right hand side over 2, I have to double the numerator, and multiplying both sides of the equation by 2 to get rid of the fractions, I get straight here. So okay, I wrote down one extra line, but sometimes it's a safer way to get there. Alright, so expanding out the right hand side, x plus 6 equals 2x minus 6. Okay, I'm going to subtract x from both sides, 6 equals x minus 6. And I'm going to add 6 to both sides. You might have done that at the one step if you want. So it's going to be 12 equals x. So I'm going to write it as x equals 12. So that I've actually answered the question. What is x? X is equal to something. Rather than what is x? Well, 6 is equal to x. It's a sort of backwards way of answering the question. Okay. Alright, question 8. I know some of you will be saying, oh, just cross multiply it. And yes, cross multiplying works here, but in my experience, many students don't understand what they're doing when they're cross multiplying. And they cross multiply at other times when it's not appropriate. For example, if this equation had a plus x here, cross-multiplying would not be correct, okay? So it's about understanding what you're actually doing. When you're cross-multiplying here, what you're actually doing is you are multiplying both sides by, for example, 6 and 24x. You're multiplying both sides of the equation by 24x when you are cross-multiplying. And the 24x over here cancels down with the 4x to leave 6 times x minus 1, and the 6 over here cancels down with the 24x to leave 4x times 5, which is 20x. Okay. Again, I think it's safer and shows a better understanding of the maths to take the moment to write both sides with the common denominator. Now, actually, also, if you do that, 24x isn't the lowest common denominator here. 12x is. So you'll end up with less fractions to cancel down in the long run. The left-hand side, we've multiplied the denominator by 3, so we'll do the same to the numerator. The right-hand side, we've multiplied the denominator by 2x, so we'll do the same to the numerator. Now that we've got a common denominator, we can multiply everything by 12x and just drop the denominators, expanding out, so we've got, I'll write out a line here, but you can do that expansion all at once. Expanding at the left-hand side, 3x minus 3 equals 10x. Collecting our like terms, so I'm going to subtract 3x from both sides, so negative 3 equals 7x, and then I'm dividing both sides by 7, and this is, so a lot of students make the mistake at this point here, and they get confused about whether they're doing 7 over 3 or 3 over 7, okay? It's about thinking about the maths and not just shuffling numbers around. In order to get x on its own, I must divide by 7, so I'm going to be dividing negative 3 by 7, okay? So x will be negative 3 on 7. Okay, and then last two examples here, some much more complicated fractions. So question 9, we've got 3 different denominators. I'm going to focus on that lowest common denominator. All 3 of those numbers go into 24, so I'm going to write every term in this equation over 24. The other place where you're potentially going to make errors here is the minus. Be really cautious about that. And I'll suggest some precautionary things that you can do to avoid making errors with that negative. Okay, so we're going to write everything over 24. The first fraction, we've multiplied, the denominator's gone from 8 to 24, so we've multiplied that denominator by 3. We've done 3 times x minus 1. Now, I'm making a really conscious decision not to expand out those brackets on the numerator, okay, and I'll show you why in a minute. The second fraction, the denominator has been multiplied by 8, so we'll do the same to the numerator. In particular, this is the fraction where I want to be cautious about when I expand out that bracket. And on the right-hand side, to go from 4 to 24, we've multiplied the denominator by 6, and so we'll do the same to the numerator. Now that we've got everything over 24, we can multiply the entire equation by 24, and we've got 3 times x minus 1 minus 8 times x minus 1 equals 6 times 3x plus 2. Okay, let's expand out all these brackets. So 3x times negative 1 is 3x minus 1. Negative 8, and you're much less likely to miss that that's negative 8 if you waited till expand out the brackets, and I'll go back and I'll show you what would have happened if you had expanded out the brackets earlier, what lots of you would have done. So negative 8 times x is minus 8x. Negative 8 times negative 8 times negative 1 is positive 8. This will be the term you'll get wrong if you're not careful about what happens, and perhaps, and as I said, avoiding expanding out the brackets until after you get rid of the denominators is a technique you can use to help you avoid making this common mistake that I'll show you in a minute. Okay, we're expanding out the right hand side, so 6 times 3x is 18x, and 6 times 2 is 12. Let's collect like terms on the left hand side, and then we'll collect them across both sides. So the left hand side we have 3x minus 8x, which is negative 5x, negative 1 plus 8, which is plus 7, equals 18x plus 12. I'm going to add 5x to both sides to keep my x term positive. Leaves me with 7 equals 23x plus 12. I'm going to subtract 12 from both sides, which leaves me with negative 5 equals 23x. And I'm going to divide both sides by 23, which means that negative 5 divided by 23 equals x. That is, x equals negative 5 divided by 23. Now, the mistake that you would have made if you had expanded things out. So if you had, particularly that one, the other brackets wouldn't have been such an issue. If you had expanded out that numerator there, so let me erase that. Don't change your solution, just watch for a minute. And if instead I had multiplied that by 8 and straight away written 8x minus 1, the temptation then, when you got rid of the denominators by multiplying everything by 24, would have been to write minus 8x minus 1. And this is not correct. This should be plus 1. And that's because when you are subtracting the fraction, remember that vinculum, the long line in the fraction, implies brackets on the numerator there. So when you drop the denominators, you need to insert those implied brackets. They become important. You're subtracting all of that, which means, oh, sorry, it wasn't 8x minus 1, was it? It was 8x minus 8. Sorry, that's not the mistake you'll make. You'll correctly expand that. But the issue here will be the negatives. So if you don't add in those implied brackets when you get rid of the denominators, you have something that's different. So if I don't have these brackets here, that doesn't say the same thing as what this does. Okay? Whereas these brackets up here aren't necessary to say the same thing. But if you're going to expand out the numerator before you get rid of the fractions, you need to be really conscious about thinking about the fact that it's minus that entire numerator. And so therefore it's minus 8x plus 8 when you expand that out. The error that many of you would make here would be to not put the brackets in and therefore end up with negative 8x minus 8 here, and your final answer won't be correct. Okay, so please be mindful of that. Please be careful about that. As I said, I think that one of the best ways you can help yourself to avoid making that error is to not expand out the brackets on the numerators until after you get rid of the fractions. Because, let me go back to what I did before. So I left it as 8 times x minus 1, which meant this became minus 8 times x minus 1. And it's much less, very few of you make the error here. When you can see that it's negative 8 times x minus 1, you don't tend to lose the negative there. Whereas you make the mistake if it's just sort of negative times the bracket. Okay, last example here. So again, we've got 3 fractions. These are much uglier fractions in that the denominators are ugly. We want to focus on writing every term with the same denominator. Now it looks ugly and it's going to require a bit of writing on this next line, but ultimately it's worth expending that time to get the next line right, because after that then things will get very simple very quickly. So we've got x plus 3, x minus 2, and x plus 3 times x minus 2. This is a little bit like the denominators being 4 and 2 and 8, okay? 8 is the lowest common multiple of 4, 2, and 8, okay? This thing times this thing gives me this thing. So therefore, that is the lowest common denominator. Okay, so I'm going to write every term in my equation with that denominator. X plus 3 times x minus 2. Take away, careful of that take away, subtraction again, x plus 3 times x minus 2 equals, just going to move the screen over here, x plus 3 times x minus 2. Okay, the first fraction, we already had an x plus 3 here, so we have multiplied by x minus 2, which means we're going to do the same to the numerator. Now you can write it as 1 times x minus 2 if you want, but it's a bit less of an issue here at this first fraction, so I don't even need the brackets there. The bigger place to be careful about it is up here. That's where we're going to make the mistake potentially, because we're subtracting that fraction. All right, the second fraction, it already had a denominator of x minus 2, so we've multiplied by x plus 3. We'll do the same to the numerator, so we're going to get 4 times x plus 3, and I'm not going to expand that out until after I get rid of my denominators. On the right hand side, we haven't done anything to that denominator, so we won't do anything to the numerator. Now we can multiply everything by x minus 3, that's x plus 3, x minus 2, and hence we get rid of the fractions. So we now have x minus 2, take away 4 times x plus 3, okay? So technically that, but those brackets don't matter in this instance, whereas if we'd expanded this out and had it written as 4x plus 12, then we'd need to be really careful about adding in those brackets around it when we lose the denominators. Equals x. As I said, one line that looks a bit ugly, but it wasn't, the maths of it's not hard, you just had to write a bit down, okay, in order to then very quickly get to something very, very nice and simple, okay. Alright, let's tidy this up. So let's expand out the brackets on the left hand side. We've got x minus 2, take away negative 4 times x, so minus 4x, negative 4 times 3 minus 12 equals x. Again, this will be the term that you'll make mistakes with if you're not careful about that subtraction between the fractions. If you collect like terms on the left hand side, x minus 4x is minus 3x, negative 2 minus 12 is negative 14, and that equals x. I'm going to add 3x to both sides, so we get negative 14 equals 4x. And I'm going to divide both sides by 4, which gives me x equals negative 14 on 4, which is not in simplest form, because 2 is a common factor there, so negative 7 on 2. Alright, solving equations with your CAS. Let's just have a quick look at perhaps, let's do example 9. So menu 3.1 for solve. You'll get to learn that key press combination. You'll use that frequently. Menu 3.1 is solve. Ask any, year 11 or 12 student, they'll be able to tell you that. I'm going to enter in my equation, so I'm going to use control divide to get a fraction template. X minus 1 over 8. Tab to get out of the fraction. So minus, control divide for another fraction template. X minus 1 over 3. Tab to get out of there or across. Equals another fraction template, control divide, 3x plus 2, sorry, not 32 plus 2, 3x plus 2 over 4. Now, your CAS, if you press enter here, it'll say too few arguments. You haven't given it enough information, okay? So the solve function needs 2 bits of information, the equation and then a comma, and then you need to tell it which variable you want to solve for. Now I know that seems trivial in this particular case because there is only one variable, it's x. Why can't it work out that I want to solve for x? Look, I don't know, but it also gives us a lot more flexibility and means the solve function is a lot more powerful in that if we have a formula, for example, ax plus b equals c, there are, 4 variables in that a, b, c and x. You need to specify that you want it to make x the subject of that. Alternatively, you could ask it to make A the subject, or B the subject, or C the subject by typing comma A, comma B, comma C, or whichever of those you want to solve for. So you put in your equation, comma, tell it what you want to solve for, and press enter. Oh, negative 7 on 23. I've made a mistake here. Let me see. What have we done? Back here. I hope you picked up my error. So when I expanded out this bracket here, it should have been 3x minus 3. So that there should have been negative 3. Okay, so that's minus 3 there, which means negative 3 plus 8 is positive 5. Okay, which means that we have 5 here, and then 5 minus 12 is negative 7, and so we get negative 7 on 23. My apologies. I hope you recognised the error before I did. Okay, some work today from exercise 1D to practice equation solving.